Hello everyone, welcome to A Light Engineer. In this video we are going to see the last video of our introduction to blockchain course, which is our Merkle Tree and Merkle Root. It is presented by me, A Light Engineer. So before we begin with the understanding the Merkle Tree and Merkle Root, I have taken a small example to explain you about the Merkle Tree and Merkle Root. So here in this figure which you are able to see, it contains the list of transactions. Transaction A, transaction B, transaction C, D and E. There are total 5 transactions that is stored as a Merkle tree. A Merkle tree is a tree data structure in which every leaf node is a hash of a transaction. See, this one is a hash of transaction. This is what leaf node, okay? And these sets are called non-leaf node. And it contains a cryptographic hash of the children's. So these are the children's and it contains the cryptographic hash of the children nodes, and these are non-leaf nodes. That is what I am saying in this figure. Now this figure shows how Merkle root is derived from the transaction. See, this one is Merkle root, how it is derived from the set of transactions which is happening in the blockchain, right? So let's begin to check how to see our Merkle root and Merkle tree in more clear way. As you see from the figure, each transaction is hashed, right? So this one HA, HB, HC, HD, HE, all are the hash of the transaction A, B, C, D, E. So hash of each transaction is hashed together with the hash of another node. For example, what I'm saying here is, this transaction is creating a hash HA. Transaction B is creating a hash HB. Now these two are merged together, that are combined together to create a hash HAB. Similarly, hash HCD. This one will be merged to create HABCD. Now this one and now this one. And here there is some logic here, right? See, this one will be left alone. Now the person who will be left alone will merge from himself, because we are not leaving anyone behind in the simple fashion. So HE will be merged together with HEE. Now we have HEEEE. Now we have HEEEE 4 times C. That is what I am saying. For example, the hash of transaction HA is combined with the hash of transaction B and hash to derive HAB. I have already explained. And in the process is repeating until there is no resulting hash. This final hash is known as Merkle root. And if you combine HABCDEE, this HABCD 4 times C, this create a Merkle root. And in the preceding example, because HE doesn't have another pair, this one HE doesn't have another pair. So where I was in the preceding example, because HE doesn't have another node to pair with, it's hashed with itself. So what I've told, it will hash with itself and create HEE here. And the same applies to HEE, right? EE 4 times C will be there, right? This will be merged. Now the Merkle root is stored in the block header. I've already explained this. There is some list of transactions that is stored in the block header, and that list of transaction will be bundled together, and that will be known as a Merkle root. Like in this I have shown you list of transaction that will be stored, and mainly it will create a Merkle root. Now in the earlier discussion I mentioned about the full nodes. In the previous video itself I have told you about the full node, light node and the mining nodes, right? So full node download the entire blockchain, and there is another type of node that is light node that download only the blockchain headers, right? Because light nodes don't download the entire blockchain. They're easier to maintain and run also, right? So what you'll prefer? I'll ask you whether you prefer the full node or light node. Yeah, it depends upon the application, which one we want to use. Either we want to use a light node or we want to use a full node. Now using a method called simplified payment verification, a light node can query a full node. To verify the transaction. Now what happened here is, since light node contain the header part, so it will query the full node, which contain set of, like it will contain entire blockchain, okay? So it will query the full node to verify the transactions, because transaction is in the entire part, like it's in the full node. So example of light node are cryptographic wallets. Now let's consider one example. Okay, by storing the Merkle root, I'll just see that whether you are able to understand this example or not. This is really excellent example, first of all. So by storing the Merkle root in the block header, this is the Merkle root. I've stored this in the block header, and block header is basically stored in the light node. Because why I'm saying like this again and again, because everything is linked together. That's why. So by storing the Merkle root in the block header and the transaction as a Merkle tree, this transaction as a Merkle tree in the block, a light node can easily verify if a transaction belongs to a particular block or not. Now, let's see with an example. Okay, I think it became complex, so I'll just take an example. Suppose a light node want to verify transaction C. Okay, light node thought that you want to verify this transaction C. Now, light node queries a full node for the hashes. So it get hash like HD it got, HAB it got, and HEEE it got. Now, what will happen? Because the light node can commute HC, light node can commute HC, and it can then commute HCD, because HD it already got, then it can commute HCD with HD. With HAB supplied, it can commute HABCD. With HEEE supplied, it can commute HABCDEEE, because we already got these two, and this will be merged to create this, and this will be merged to create this Merkle root. Now, because the light node has a Merkle root of the block, it can check to see if two Merkle roots match. Now here, after getting this and this, we are getting two Merkle roots match. If they match, the transaction is verified. Yes. So, as you can see from the simple example, to verify a single transaction out of 5 transactions, like we already have a 5 transactions in the previous one, A, B, C, D, and E. How much hashes we require? We require 3 hashes. That will be retrieved from full node. So mathematically, for n transaction in a block, we require log to n hashes to verify that transaction is in a block. For example, if there are 1024 transactions in a block, a light node only needs to request 10 hashes to verify the existence of a transaction in a block. So this is really very awesome, right? So in this series of video, we have learned about the motivation behind the blockchain and the problem that it aims to solve. You would also have a chance to know how blocks are added. I've already shown you in the previous videos of my mining, like how blocks are added to the blockchain. In the next phase of a video, we'll learn how to build our own blockchain using Python, so that you can see and understand the inner working of a blockchain. Thank you for being a part of this blockchain course, and hereby we conclude our introduction to the blockchain. Regards, a light engineer. Meet you in the next video. Thank you. Keep learning, keep earning.